Hello everyone, I'm Chenxi from Nanjing University. The authors of this paper cannot give the talk today, so I will give the presentation instead. I don't participate in this work, so if you have any very detailed technical questions, please contact me offline and I will pass them to the authors. The title of this talk is Two Approaches to Fast Bytecode Frontend for Static Analysis. Let's start with the background. Program analysis is a mature field with applications like security analysis, compiler optimization, and program understanding. All of these are powered by the static analysis framework. So what does a framework need to do? In a general workflow for program analysis, we usually go through several stages. After input program, first, translating source code into an intermediate representation. Second, running fundamental analysis, such as code graph construction. Third, running client analysis, such as vulnerability detection or test analysis. And finally, getting results, such as a vulnerability report. Almost all analysis frameworks, including this classic static analysis framework for Java, need to support both IR frontend and fundamental analysis. In other words, the IR frontend is indispensable. So why do we need a new frontend? The efficiency matters. In many cases, researchers want to run analysis quickly and get results fast. A faster front-end directly speeds up the entire analysis workflow. However, the existing works are still too slow. Existing front-ends are even slower than the subsequent fundamental analysis. Like RTA take only 49 seconds on a benchmark, where current front ends take longer just to translate IR, but will only take 4 seconds. We built a new and effective front end and compared to the existing works, our front end is on average 10 times faster and up to 600 times faster in some cases. We achieved this through two new approaches, and I will explain shortly. Our implementation is based on a Tai-e framework, and we provide an open source artifact. Now let me introduce our design. A typical front end goes through several stages, like crossword construction, class hierarchy construction, the three address code translation, and type inference. On this, the last two steps are the most complex and time-consuming. First, in the three address code translation step, we need to translate Java bytecode into the three address code. This step has two key challenges. The first is the bytecode data flow is step-based. For example, the statement a equals 1 means push the constant 1 onto the stack and then pop it from the stack to store it in the source 0 corresponding to variable a. And the second is different variables may share the same variable slots. For example, when computing the variable c, it may reuse the same slots that variable a used. This makes its data flow is quite different from the typical data flow. We can't directly get the value of variable c from the bytecode. We have to follow the stack to check the data flow. For this problem, we propose our first approach, pattern-aware three-address code translation. Specifically, the bytecode defines two different use patterns, A and B. For pattern A, the right edges in the figure represent the stack defined use. For example, in the second line, A equals P, it corresponds to the first right edge on the right. This line compiles into two bytecode instructions, I0 and I1, where 0 and 1 represent the slots storing variable P and A. This instruction means that the value is loaded from source 0 and push it onto the stack, and then pop from the stack to store into the source 1. This is the stack-defined use. For pattern B, the blue edges in the figure represent local defined use. For example, before in the first line, A equals A81, source 1 already stores the value of variable A. We then load it from the source 1. And when you use in the first line, this is a local defined use. If you are still not very clear, if you are still not very clear, we can just focus on the structure of the red and blue edges. For pattern A, there are no back edges, which means the definition of variable of a variable always before its use. In contrast, pattern B may has the back edges. In this case, loop can make a variable to be used before it's defined. So what problem does this cause? Without the back edges, we can generate 3AC in one pass using reverse post-order traversal. It's simple and fast. So in our approach, we use different methods to handle the different pattern. For pattern A, without the back edges, we can use one pass to generate 3AC. It's simple and fast. For pattern B, it may have the back edges. We handle this by inserting 5 nodes to translate it into the SSA form, which removes the back edges. We use the standard SSA algorithm. In this process, we only need to handle about 20% bytecode instruction, so it's very fast. After removing these back edges, we can use the one pass again. In summary, our approach is to handle simple pattern A using a fast and simple method A, and handle complex pattern B using a complex method. However, existing works use only one complex method C, a single method, to handle all patterns, include the simple pattern A and the complex pattern B. This makes they have the redundant computations, which slows down their translation. Now we have translated the bytecode into the 3-address code. However, this 3-address code doesn't have the type information. For each variable, we don't know its type. It's marked with a question. Because the bytecode is untyped, naturally the resulting 3AC is untyped. But the type information is important for analysis. Missing the type information, for example, it may cannot resolve the method calls precisely. So we need the type information. So we need the type inference to get the type information. In general, type inference is viewed as a constraint solving task. For example, for this case, in the 3-address code, the statement A equals new hash map means that the hash map is a subtype of A. Similarly, tree map is also a subtype of A. For the statement B equals A, we know that the A is a subtype of B. For invoke statement like B point map points clear, we can infer that B is a subtype of map. Based on these constraints, we can build a type constraint graph. And we can also get the program's type hierarchy in advance. So how does existing SootUp algorithm handle this? They start from the root nodes and follow the arrows. Since the types of the hash map and the tree map nodes are already known, they don't need to handle. When handling variable A, since A is a parent type of its predecessors, they need to find the least common ancestor, the LCA of those predecessors in the type hierarchy. So the type of variable A may be the map, serializable, or clonable. For variable B, because it's the parent type of variable A, its type may also is the same 3 types. When they handle the last node, the variable A and B each have the 3 types. However, according to the constraints, B is a subtype of map, and variable A is a subtype of variable B. So the SootUp algorithm finally filters out the redundant elements and gets the variable A and B is a type map. During the traversal, many redundant elements are computed, which slows down their process. For this problem, we propose our second approach, pruning-based type inference, to handle it. So what's different with the SootUp algorithm? When we handle the variable A to get its results, we use the constraint to filter the results early. And during the traversal, we don't have many redundant elements, which reduce the redundant computation. It makes our approach faster than the SootUp algorithm. Even if pruning still multiple associates, we simply choose one non-deterministically. Why is reasonable? In our paper, theorems 4.1 to 4.4, we formally prove that most programs satisfy a property ensuring our algorithm is correct. Due to the time limits, I will not go into detail, and the experiments show that our algorithm produce no incorrect results. So how does our frontend perform in practice? We built a large and diverse benchmark and compare our frontend with the most popular and well-established static analysis framework, Soot, WALA, and SootUp. For efficiency, our frontend significantly outperforms all others, both in three-address code, translation, and in type inference speed. Specifically, our frontend is on average 10 times faster and up to 600 times faster. Reliable is also important for frontend. It affects the backend analysis. In terms of reliability, we also perform the best, successfully processing all input bytecode methods. Finally, our frontend is implemented in Tai-e framework and will be released soon. If you are looking for a faster and more reliable frontend for Java, welcome to learn and use Tai-e. In the upper right is the QR code of the Tai-e website. If you have any detailed technical questions for our frontend, you can contact me offline, and I will pass them to the authors. Thank you. That's all.
Take some questions.
Thanks for the talk. First, my question is that is your three-address code in the SSA form?
Yes.
What is the difference between your algorithm and the memory to SSA algorithm and RVM? Do you know memory to SSA?
Oh, I don't know this mean.
Oh, I see. So that's an algorithm that if you store variable to the local stack or local memory, and then like every time you load from the local memory is a use, and then that's a defined use. Then you can use the standard SSA construction algorithm to construct the SSA form. Oh, okay. Maybe we can discuss later. Yeah.
Okay. Thank you.
I just have two questions for you. So one of them is when it comes to the type inference, how do you determine the dynamic generated object?
Dynamic?
Yeah.
Pardon? Dynamic?
Dynamic generated. Yeah.
Dynamic generates.
Sometimes through the reflection.
Oh, I don't know this detail because we generate the constraints advance our analysis.
Okay. Another question is about because the most Java applications is like large scale applications. So how do you transfer to your optimized IR to bytecode of the large scale applications? Something IR. Like a Spring we used in realistic world. Because I'm considering how to leveraging. If we try to leverage a framework to optimize, you have to a way to transfer back to the Java bytecode. Yeah.
Oh no, we can't to transfer it to back the bytecode for IR.
Okay. So because I'm considering because like when it comes to the Soot, you can compile, convert original IR to get back to the bytecode.
We don't provide
and to get that from there to for optimization, further optimization. Yeah. Okay.
Thank you, Mei Long.